Hi guys, now we continue lecture for week 3, Soil Mechanic CEG243. Chapter 1 or topic 1, Physical Properties and Classification of Soil. So for week 2. As usual, this one is program outcome. This is course outcomes and CO mapping. Alright, so we go for the learning outcomes. At the end of the lecture, students should be able to understand type of soil based on particle size, for example, gravel, sand, silt, and clay, determination of particle size distribution and grading characteristic, sieving method and sedimentation methods. Second, soil description based on visual examination and simple tests. And the last one, soil classification for engineering purposes. Soil classification system based on British or Malaysian standard. Alright guys, types of soil. Soil can be classified into two major groups. First group is coarse soils, also we call as the cohesionless. Coarse soils are classified as having particles more than 0.063 mm, such as sand and gravels. The grain either be rounded or angular and usually consists of fragments of rock with iron oxide, calcite, and mica presence. Alright, this one is shape of coarse grain soil particles, for example, rounded, sub-rounded, angular, subangular. Okay, second type of soil is fine soils, or we call as the cohesive. Fine soil are finer than 0.06 mm and typically flaky in shape, such as silt and clay. Very fine oxide, sulfides, and sometimes organic matter may be present. This one is example of silt and example of clay. Let's refer to the description for cohesive and cohesionless soil. Alright, so for cohesive, this is a fine grain. Cohesionless is coarse grain. Okay, for cohesive, silt and clay, for example, flaky in shape, impermeable soil. Good load bearing capacity, changes in moisture do not significantly affect the volume changes. However, for cohesional soil, for example, gravel and sand, rounded or angular particles, impermeable, very good drainage quality, poor load bearing capacity, changes in moisture strongly influence the volume changes. This is an example of rock based on the size, particle size. Okay, for example, here boulders, the diameter is more than 256 mm. For sand, the diameter is about 0.063 to 2 mm. And for gravel, 2.64. And you can refer to cobbles and also silt. Alright, so first we go for the soil description and soil classification. Description is simply what you see and how the soil responds to simple tests. Okay, this is a simple and universal scheme for soil description. It's as follows. First is nature of soil grain. We look at the size, grading, shape, surface texture, and their mineralogy. Current state of soil. Which is current stresses, water content, and history of loading and unloading. The structure of fabric, layering or bedding or fissure or jointing or cementing. Okay, it depends on the structure of fabric. The formation of the soil may be deposited naturally by water, ice, or wind, or maybe by residual product of rock, weathering, or maybe be compacted by machine into embankment and fill. Okay, now we go for the soil description through field identification. Okay, first is particle size by implementing visual examination and field grading. Either soil is well graded, poorly graded, uniformly graded, gap graded, and so on. Compactness, sometimes regarded as field strength, can be reported as loose, dense, or slightly cemented. And structure, either soil is classified as homogeneous, interstratified, intact, or fissures. Right? Next is cohesion, plasticity, and consistency. This method can be used to identify soil particles by hand squeezing. Soil can be classified either very soft, firm, very firm, hard, or crumbly. Okay, dilatancy. Dilatancy will exhibit a glossy water film marking on the surface on the bed. Dry strength can be identified by breaking the soil. Weathering can be classified into unweathered, slightly weathered, highly weathered, or fully weathered. Alright, this one is well graded and poorly graded, and how we classify is as poorly graded or well graded. For well graded, a soil is in order to be classified as well graded must have a good range. All representative particle size between the largest and the smallest. Look at that. This one is well graded from the largest to the smallest. Poorly graded soil are either those containing a narrow range of particle size or those with some intermediate size lacking. Soil with a limited range of particle size are called uniformly graded. Soil will have some intermediate size or size not well represented or missing are called gap graded. Okay, this one is poorly graded. If you see it, this one is narrow range and particle size. The size is no, it's not just like well graded from the larger to smallest. This one is missing, mix up. Okay, this one is uniformly graded. You see the size is quite similar, and the gap graded is we missing some represent size here, so we call it as the gap graded. Alright, this one is example of visual soil classification. Okay, if you see here the color, we can see the color by naked eyes. Brown color, no odor, texture is coarse. Major soil constituents is gravel, minor is sand and fine, and then you have to calculate and to measure, to weight the weight of soil, gravel, sand and fine. Look at this. Okay, and then we have to determine the you have to find the gradation as well graded, particle shape, sub-rounded, and then you have to find the moisture content, the moisture condition, whether that one is moist or dry. And this is example of classification as gravel, brown gravel, some sand, trace, fines, well graded, sub-grounded, and dry. Okay, now we go. What is the soil classification? Classification is a scheme for separating soil into broad groups, each with broadly similar behavior. There are various classification schemes for different purposes. For civil engineering purposes, soil classification should be mainly on mechanical behavior. For soil classification system, we have three systems: BS1377. Method of test for soil for civil engineering, BS5930 Code of Practice for ground investigation, ASTM American Society for Testing and Materials Unified Soil Classification System. Figure below give a general overview of the British Standard Range size particles and American Standard Range size particles respectively, which are carried out based on weight percentage falling within the band size represented by distribution and subdivision. If you see here, for British Standard, the fine size is less than 0.06 mm, while for the ASTM is 0.074 mm. Alright, so this one is latest version of cost of fine composition percentage to name soil type. Okay, give you an example here. This one is example: sand is 60%, gravel is 30%, silt is 10%. Okay, look at the table. Okay, this one is principal soil type, this one is secondary constituent. So based on the percentage here, example, principal soil type is sand, secondary constituent is gravel. So how to name the soil? First, you look at the gravel. Gravel is 30%, is more than 20%. So the name will be very gravelly. So how to name? The soil is silty, very gravelly sand. Alright. Another example, if you have the gravel 90% and then you have sand 10%. Okay, sand is 10%. So means that just sandy. Okay, so it is going to be sandy gravel. That is how to name the soil, right? Alright, this one is ASTM or Unified Soil Classification System. This one is table manual for uh, fine soil classification. This one is a plasticity chart. Alright, so okay, you may refer to the table here, USCS. Okay, particle size analysis aim to measure the distribution of particle size in the sample. When wide range of size is present, the sample will be subdivided and separate tests carried out on each subsample. Alright, so for type of particle size analysis, two procedures for obtaining the particle size distribution of soil are sieve method and sedimentation methods. Sieve method is used for gravel and sand size, particle, but cannot be used for silt and clay size. Two types of sieving method are wet sieving test and dry sieving test. Sedimentation method, we call as the hydrometer test, is used for fine grained soil. However, at the end of the analysis, this test cover the quantitative determination of the particle size distribution in the soil from the coarse size to fine size. Hydrometer, this test is done when the percentage of fine grain in dry sieving analysis or wet sieving analysis contain more than 10%. Okay, look at this. This one is sieving method and this one is sedimentation method. For the soil size less than 0.06 mm, okay, more than 10%, so you have to do the sedimentation method. And the rest is you have to do the sieving method. Okay, because this one is for gravel and sand, this one is for silt. Silt is for sedimentation, silt or clay. Alright guys, this one is a procedure for wet sieving, so please check out and read the procedure one by one, step by step. Okay, the detailed procedure of wet sieving can be referred in BS 1377 1990 clause 9.2.4. Alright. Okay, this one is dry sieving test. Dry sieving is carried out on particle bigger than 63 μm to determine the coarse material in the subsample in accordance to BS 1377 1990 Part 2, Test 9.3. The subsample is first oven dried to make sure that there are no moisture. Feed the largest size test sieve appropriate to the max size of the material present to the receiver and then place on the nest of the sieve. Okay, this test is very simple actually. What you do is first you have to weight the sample of soil and then you place the sample on the nest of the sieve. Alright, and then you shake the shaker here. Okay, and then after that you determine the weight retained on the each sieve. You have a different sieve with a different size, okay, with different size, so you determine the weight retained in each, and then you have to determine the cumulative percentage passing to plot the grading curve. Okay, you may refer to this YouTube video also. Okay, this one is a hydrometer test for particle size smaller than 0.06 mm in diameter. Okay, based on principle of sedimentation of a soil grain in water. So you have to study and learn how to conduct the hydrometer test. Yeah. Alright. Okay, actually this one is the sieving testing procedure and then the sieving apparatus. Okay, if you see here, small aperture to the big aperture. This one the size is bigger and then this one is smaller. Alright, and then you have to take the weight of the mass retained at the top here and then here and here and here, and then you have to do the analysis. Okay, this one the test is actually simple. Okay, you just follow the BS standard procedure. Particle size distribution sieve analysis. This one is the table that we are going to use to analyze the sample of sieve analysis. Alright, if you look at here, this one you have stage 1, stage 2 and stage 3. If you have a many stage, you have to do refill correction. Alright, this is the equation for refill correction. Okay, look at this. This one you have a sieve size opening different size. At the top is larger then the bottom, the last one is 0.063. Okay, all right, look at this. This one is mass of sieve and soil, mass of soil. To determine the mass of soil, you have to minus the mass of sieve and soil minus with the mass of sieve. You will get the mass of soil retained, and then corrected mass retained. For the stage 1, there are no correction. Alright, to determine the percentage retained is corrected mass retained divided by initial mass used times 100. So you will get the percentage retained, and then cumulative will be start from 100%. And then 100%, and then you minus with the percentage retained, you will get the cumulative percentage passing. Okay, from 100% to maybe this one is 0%. Alright, this one is how we measure the size of the sieve. Okay. Okay, example here, after you conduct the test, what you do is you have the mass retained here. Okay, so what you have to do is you have to weigh the retained soil on the test sieve for each sieve. Alright, the mass of soil retained can be obtained by deducting the mass of test sieve obtained on early stage of testing. Alright. Alright, for analysis, okay, grading characteristic. First of all, 3 points are located on the grading curve. So for after you determine the value of cumulative retain from the table, you have to plot the graph. From the graph, you will see the D10, D30, and D60. Okay, alright, so D10 is the maximum size of the smallest 10% of the sample, like that lah. And then you have to determine the effective size. Effective size is D10. And then uniformity coefficient CU is D60 over D10, and then you have another equation which is CG D30 squared divided by D60 times D10. Okay, this one is used to determine the grading characteristic. Okay, this is the grading curve that I'm talking about. We have the percentage finder, 10%, 30%, 60%, up to 100%, and then you find the value of D10. Okay, from the 10% you plot and you will get D10, D30, and D60. Alright guys, you refer to the equation example here. Total mass of soil used is 2458 gram, and now you have stage 1 and stage 2. Okay, you have the sieve size and mass soil retained. So what you do is you have to insert into the table, and then you get there, look at here, you have a pen content and refill sample. Alright, so from this example, okay, we look at the next slide. We're going to fill in all the information just now from the example into this table, sieve analysis, particle size distribution. Alright guys, this is the solution. Alright, so you look at this. This one is initial mass of dried soil use. Okay, this one is stage 1 and this one is stage 2. So you have to fill in all the information. Okay, so for first stage, there are no correction mass retained. Alright, this one is mass of soil retained, and then this is no correction, you just fill in all the information, and then to determine the percentage retained is 55 over 2458 times 100, you will get 2.2. Alright, so 100 divided by 2458, you will get 4.1. So to determine the cumulative percentage passing, start with 100% minus 2.2, you will get 97.8, minus 4.1, you will get 93.7. Okay, so you do the same thing for the rest. And then for the stage 2, okay, refill sample use is 196. Okay, if you see here, soil passing is 1165. So means that there are you have to do the refill correction. So refill correction is to determine the refill correction is 1165.0 divided by 196, you will get 5.94. So for stage 2, you have 54.3, you have to times with 5.94, so you will get 322.8. to determine the percentage retained, 322.8 divided by 2458, you will get 13.1. So from this one, 47.4 minus 13.1, you will get 34.3. So you do the same thing for the rest. Okay, if you see here, the value of the total is 2457.4, which is less than 2458. Maybe some of the sample is written on the pen. All right. So sometimes you're not going to get 100%. Sometimes you will get 99.5%, something like that. All right. If you have the stage 3, you do the same thing. Okay. So you just take the refill sample use, and also surpassing. See, surpassing divide by refill sample, and then you will get the value of y, and then you have to times with 5.94, and then you will times with the mass of soil retained. You will get the corrected mass retained. All right. Okay, refer this one, calculation for table, mass of soil retained, mass of sieve per pen, and soil minus with mass of sieve pen only. Alright, corrected mass retained, the value for first sieving is the value of mass for soil retained. For second sieving, corrected mass is mass of soil retained times refilling correction. Okay, so you will get this one. For the third sieving, corrected mass retained is mass of soil retained times refilling correction. For refilling correction, you have to use A over B times D over E. Alright, so percentage of retained, corrected mass retained divided by initial mass of dry soil used times 100. This is what I'm talking about. Cumulative is 100% minus percentage retained. Okay. This one is only to use to calculate for the first value lah, and then you have to refer what I'm talking about just now. And then from the data you have just now, you have to plot the grading curve. It's a graphical representation of the particle size distribution to describe the soil. Okay, you see here, this one is percentage passing and this one is particle diameter size, right? Okay, from the example just now, you will plot the graph. So you get something like this, right? So based on percentage passing versus particle diameter. Okay, this one is typical grading curve. First is a polygraded. Alright, so second is well graded. B. C is gap graded because sum of the value is not. You don't have the sum of the value for the sum of the size. Okay, D is sandy silt, perhaps a deltaic or estuarine silt. Okay, this one is actually D and E is not common, but usually for A, B, and C. This one is very typical grading curve you always use. Just now you have a sample, you have to fill the tables, and then you plot, and after plotting you find the 3 point allocated on the grading curve. So you have D10, D30, and D60. You have to determine the effective size, coefficient uniformity CU, coefficient of gradation CG. Okay, this is the question that you have to know lah. Okay, this is from the grading curve. Alright, this is what I'm talking about. From the D10, so you will get 0.27. From D30, you get 1.6. D60, you get 5.3. So from this value, you have to calculate CU and CG and D10. Alright. Alright, this is the grading characteristic, D10, D30, and D60. So what you do is you calculate the CU, so you have 90.6, and then you calculate the CG, 1.78. So, and then after that you have to check the grading characteristic. Alright, the next step is do the calculation for composition, gravel, sand, and silt. Okay, how much is the gravel, sand, and silt from the graph? Alright, and then we have to check for the grade, and you have to refer to this one. Other than that, CU is more than 5, CU less than 3. Other than that, is categorized as the polygraded. 0.5 between CG is between 0.5 and 2 is well graded. CG less than 0.1 is cap graded, and other than that is polygraded. Okay, however, if you want to know whether that one is well graded or polygraded, for well graded, CU and CG must be well graded. Okay, if one CU is well graded, CG is polygraded, so it's classified as the polygraded. Okay, classification of soil. Soil is first is well graded or uniformly graded or cap graded, and then after that is tertiary constituents type of soil. Okay, for example, you have gravel here 60, sand is 30, and silt is 10, so it's become silty. And then secondary constituent, okay, silty, sandy. And then the last one is principal soil type. Okay, principal soil type is the largest number of percentage, so gravel. Okay, for example, well graded, silty, sandy, gravel. Okay, that one is example. However, you have to check for the secondary constituent. You have to check the table whether that one is slightly sandy, sandy, or what. So you have to refer from the table before I show you, right? Alright, this is what we're talking about just now. You just refer here again. Alright, how to determine the composition, percentage of gravel. For example, gravel is here from this line. Okay, gravel is 100% minus this one is 33.5. So it's 33.3 or something like that. So you just refer from the graph here. So it's become 65.7, and then this one is sand. Okay, from this point to this point. So so you have 33.5 minus 0.8% silt. So you will get the composition of the soil here. Alright, from the grading curve composition, gravel is 100 minus 34.3, 65.7. Alright, so you also may find from the table of calculation, but also usually I will refer to the grading curve. And then sandy is 34.3 minus 0.8. This one is actually I already explained to you. Alright, so silt is 100 minus 65.7 plus 33.5, so you will get 0.8. Alright, now we're checking for grade. Cu is more than 5. So it indicates that it well graded soil. CG is 1.78. It's between 0.5 to 2. It indicates that well graded soil as well. So soil is classified as well graded, okay, sandy gravel. Whether that one is slightly sandy or very sandy, you have to refer to table. Since sand is more than 20%, so it classified as very sandy. Alright, okay, so you may refer to this table. Okay, secondary constituent is more than 20%, so this one is very sandy. Alright, if the value percentage of sand is between 5 to 20, it's become just sandy. If less than 5, it's become slightly sandy. Alright, thank you guys. Hard work matters. There are no secret to success. It is the result of preparation, hard work, and learning from failure. Thank you.